Not even happening. Okay. This is why the quality of these videos is not premium. Let me tell you that much. So I missed one day. The recording just disappeared, and you can blame Zoom for that. That's not my fault. I mean, technically, it might be my fault, but I don't know how. But I hope folks are using that when they feel it's appropriate. If you ever miss a class or you have any questions, you can always go back. I've had some people come to office hours now, but not that many. So I'm assuming you all get it, or you need different office hours. Which one of the two? Raise your hand if you get it. Raise your hand if you need different office hours. Raise your hand if I'm intimidating and you don't want to talk to me. Okay, that's pretty. Hey, I like some honesty. That's okay. So how do I trick you into coming? Should I put more snacks in my office and then you'll come in and eat? Okay, I know that works for some folks. Yeah. Okay. All right. All right. I'll go to CVS and just get a shit ton of snacks. Try not to eat them all. Yeah. We can't support Trader Joe's anymore. They're anti-union, and I don't fuck with that. Okay. So let's go to. I know that it broke my heart because I'm very much into eating snacks. Trader Joe's has premium snacks, but they don't have premium people who run the offices. Okay. What's that?
My sister stopped supporting like Starbucks and that whole house and everything.
Yeah. Yeah, lots of boycotts going on. So this is still here, and Gonzalo may or may not be telling us about 8.1. Now, if I recall, let's put what we had up here. We were doing this problem, and as far as I remember, I think everyone got it, right? Just the part A. I mean, this is an interpretation part, right? You just need to write words afterwards, but you are all able to get RK4 to work, right? We could have Gonzalo go through these types of integral solutions where we change it. And that essentially leads us into differential equations of more than one variable. But I was very curious whether or not we should go back to that problem, which has the data itself and construct the derivatives from the data. Did people, raise your hand if you finished that and you don't want to go back to it. So this would be the problem. So I promised you on Monday, it'd be this problem, 523. I said, oh, if we have time, we'll come to it. But we kind of just like ran up to the end of class, right at the end of it there. So my heart is telling me that we should probably just finish this problem here before we jump into 8.2. And then if that's okay, Gonzalo, I'll actually slide you and everyone down one step. Is that okay? Next on Monday instead?
Yeah, I think that would be best. It would give you a nice window to prepare.
Okay. So then what I think we should do here is I think we should, because derivatives are going to be so fundamental to understanding what we're doing for the next 3 or 4 or 5 weeks, it's really important that we understand both how to take them with respect to arrays, with respect to data that already exists, and then also to really understand the different types of approximations that we can use. And I think it's important to go back to 525 and finish this problem first. And just to remind people what we were doing here, I'm going to pull the problem back up. We're going to pull that data back up. So if it's possible, maybe get into the groups that you had last Wednesday. Yeah, last Wednesday. So that's the 21st. And what we're going to be doing is we'll talk about the problem because I kind of showed you the problem, broad stroked it, and then just let you go. But I think we maybe only had 30 minutes. So we'll break down the problem a little bit more, knowing what we know now about how to do these ODEs. And we're going to apply it here to the context of this problem. And if we finish in time, great. That'll allow us to talk a little bit more about RK4, answer any questions about that before we move on. Because for basically 5 more weeks, we'll be using RK4. And if you do a problem, which you should start thinking about, we'll talk about that in a week or two. If you do a problem that does anything that has a time evolution or watches something go from state 1 to state 2, it's going to use an RK4 as well. Does that make sense? Okay, so let me pull up then 523. And while I'm doing that, do you mind getting back into the groups that you had and pulling up whatever code that you had already started for 523? And if you weren't in person, that's perfectly okay. I think, there's some people missing and there's some people extra. So we're just gonna wing it and put together what groups will help us solve this wonderful problem. I believe Zori is skiing. Yeah, she left and she's like, I'm going snowboarding. I was like, what the fuck? Well, that's awesome. Good for her, but I'm jealous.
But we're gonna go up there.
Okay, that's perfect. Just yeah. Wait, are you a 3? Who's a 3? Okay. And do you want to just jump in? Is that okay? Oh yeah, perfect. Okay. So let me just quickly showcase what we're gonna do, get our brains up and running again. And I do want to take this opportunity to really talk about the importance of planning before you start. And so I always yell at people because there's no paper in front of you. And I really recommend there being paper. So my paper is green and it's vertical. Your paper should be, well, not necessarily white, but whatever paper you have in front of you, it could be your iPad. And what you want to do is you want to have a game plan before you start. Okay. So I'm going to try and demonstrate the game plan that we'll create for this, and you can compare it to the one that you would have made. Okay. So let's read this problem together. Image processing. And the stem, I don't know what that means. Okay. So when light strikes a surface, the amount of falling light per unit area depends only on the intensity of the light. Sorry, not only on the intensity of the light, but also on the angle. Okay. So if it falls at an angle, you have less light than if it falls directly on it. So you have this beautiful picture here what the light sees, and the intensity of the illumination is this A cosine. Okay. So this is the central element of 3D computer graphics. It allows us to calculate how much light falls on a 3-dimensional object and how they'll look when illuminated from various angles. So for example, you can see my face, hopefully, and you can see that parts of my face are shaded and parts are not. That is due to the fact that my face is not perfectly round, but has, peaks and troughs. And so the angle at which the light is hitting, let's assume that that's the only light in this room, right? Bouncing off my nose will look different here than here, where it's only glancing, right? Okay. So we could imagine if we were looking down on the earth from above and saw mountains, you would know that the mountains have some altitude, right? So let's say the mountains look like this, nice triangle. And depending on the angle of the light, right, you could imagine that one half, if I put the light source over here, then one half of the mountains would be in shadow and one half would be fully illuminated, versus if it was above, it would be fully illuminated from the top, right? Okay. And there's some fun little math in here, which I'm not going to make you understand or even care about. You don't have to care about any of this. We're going to come back to this in a few seconds. In practice, you can read through this and try to understand it, but let's look at what the instructions say first. So it first says on the online resources, you'll need a file called altitude, which has the altitude. They define it as W, X, and Y in meters above sea level on the surface of the Earth, measured on a grid of points. Okay, so I'm already thinking about this data, and I'm imagining that it's some array, right? And at every location on the array, okay, here is W of X and Y. Does that make sense? Okay, so you pulled that data down. Anyone not have that data on their computer? Okay, good. You then need to calculate derivatives, dw dx and dw dy. So if I had a function, f of x, how would I write the derivative on a computer? Say a forward difference. They don't all talk at once. F of x plus h minus f of x over h. Okay. Reasonable? What else is this known as? So you just make a few modifications. This is the fundamental theorem of calculus, as long as h becomes infinitesimally small. But of course, we don't have the most brilliant computers ever invented, so h cannot do that. So this is an approximation. Okay. And this is the forward difference because I go forward. I could just as easily have made this f of x and this of x minus h, and that would be called the backwards difference because I'm going backwards. What does the centered difference look like? Is that correct? Are you looking at it? Yeah. All over 2h or h? Okay. Is that correct? Over h squared? Is that true? And are the signs right? Are the signs right? Do you know where to find this in the textbook?
Page 91 plus fx.
plus fx here?
No.
This one?
Yeah.
Ah, interesting. Okay. Okay, which one was better? Which one is better? Which one is a better approximation to the integral, to the derivative? Sorry.
So
what's that?
the bottom one is the second derivative?
Is it?
It looks like it.
Okay, so let's double check here. Okay, this is called the centered derivative. Let's go back up. Let's find out where this all comes from. And let's see what mistakes we made. Okay. That's interpolation. I don't need that. All right, here's partial derivatives, which we actually didn't get to. There's the second derivative. That does look like the second derivative. It doesn't look like the centered derivative, does it? Okay. What does the first derivative look like? Well, the first derivative looked like here we go. Can you see the difference? A central difference looks like f of x plus 1/2 h minus f of x minus 1/2 h all over h. And this one here is the second derivative. Okay. You don't have to have memorized that, but let me show you some of the ways that you knew that you were right or wrong. Okay. In a derivative, these are slopes. How many points do you need for a slope? 2. And look, I only need 2 points here. The presence of a third point told me that this was a second derivative because it's a curve. It's talking about the curvature, right? Okay. This one looks like it's centered too. So that might be, in our minds, we might be thinking to ourselves, well, that's centered around h. And that would be true, except for it's the second derivative around x, right? Okay. So this is what you have when we're talking about a function, f of x, right? Is it possible now to take derivatives if you don't know what the generating function is and you only have the data? Because that's what we're essentially going to do here, right? I go back down to 523. Yeah. Here, it doesn't tell you what the f that creates all these altitudes are. And yet, it expects you to take derivatives. So how would you do that? What's that? It gives you the locations of x, yeah. It gives you the locations of the value. In this case, we're going to use w. And I do know how far away they are. So I know that they are h away from one another. Yeah.
So first we start by using those values to find the equation, or the function, for the line, and then we find the derivatives from there.
Okay. I love the idea, but you don't have to do that much work. You can just guess from the data itself. You don't even have to find the function. Okay, so follow me on this one. If I'm here and I want to find the slope, I have one point where I am. All I have to do is point in whatever direction I want to head, and that is the derivative in that direction, at least for the next point, right? at least in this circumstance, right? This is just the difference between the next point and where I am, right? Divided by h. Make sense? Okay, so if I were to take this data, and I'm using W data now, and I want to write, okay, W of X and Y, okay? And now I want to do a derivative with respect to X. What does that look like? You choose. You have to choose. I don't know. Okay, central. Well, I don't have an F. I only have W. I have to be careful. Okay, W of X plus H over 2, comma, Y. Good. Minus. X minus is 1 over 2, comma 1. Okay. Right, right. All right. So I would love that, except we have some problems. Okay. So because we can't arbitrarily choose H is chosen for us. So let's say I have this data and I have these points here and here and here and here, right? And let's say those are all HOA. I can't pick this one, right? So if I convert, let's say this is X going that way, Y going this way. The values that I have in my computer start at 0, 1, 2, 3, because they represent pieces of the array, right? And so what I have here at X and Y, it's not really an equation, right? I'm not actually putting in X and Y and then it does a calculation and it spits out W. It's just telling me in my array, what are the values of the altitude at every location. So I have this and the nearest neighbor, and I can't choose in between. But I can still do this as long as I make my H twice as big. You see? So I can grab information from my nearest neighbor, but if I set, H to be this length, then it still works. Does that make sense? So I can write this 2 ways, okay? And I'm going to convert some of these letters. So this is going to become I, and it'll be an index 0, 1, 2, 3. This is going to become J, and it'll be an index 0, 1, 2, 3, okay? So I and J are going to take values of 1, 2, 3, all the way up to however big the array is. Okay. And H, I need to convert into the coordinates that are in the array itself. So I'm only going to go backwards and forwards 1 step. That make sense? So H is going to become 1. In this case, it's actually going to become 2. Yeah, because we wanted to use essential difference.
If it was forward, it would be 1.
Yeah, if it was forward, it'd be 1 here and then nothing here, and then 1 down here. Okay. But the thing we have to make sure of is that this H is still represented in the data itself, right? Okay. So then this becomes our I, and this becomes our J. So I could rewrite this. I could say W I plus 1, comma, J, minus W I minus 1, comma, J, all over 2. And that's a perfectly good way to write the exact same derivative, right? If you wanted to do just the forward difference, you could say W I plus 1, comma, J, minus W I, comma, J, and then you wouldn't even need to divide by 1, but it's the same, right? Now, one of them will be different than the other because they use different information. So if you use one version versus the other, I don't personally have a preference. But I will notice that you will run into a problem. Okay? Regardless of how much fun you're trying to have here, there are edges to this picture. So we will have to treat them differently. Because as I look at this picture, if I'm taking the derivative, let's say I'm doing a forward difference or even a central difference, here, when I'm on the edge, I can't subtract backwards, right? And similarly, when I'm on this edge, I can't subtract forward because that value doesn't exist. So what I'll need to do is only calculate. I'll need to only calculate the derivatives for the stuff that's inside, or on the edges, I'll have to be very careful about only doing it in the direction that I have information. And I'll accept either one of those. So going around the edge and being careful about which direction you take it is the right answer, but I'm not going to be a stickler about it. Does that make sense? Okay. So then you need to know the value of h. And at the very end, it says the distance between meters, or in meters, which is about 30,000 meters in this case, between each of the grid points. So this one would have been 2h. I'm going to 2 times 30K. Here, 30K. Okay. And that'll just make the numbers actually reasonable because the altitudes are very large. Okay. So that's the theory. And I would write that down. I would draw myself a picture so that I understood what I was doing. And now, how do I construct the code? Okay. So the very first thing in the code is always the same, and it has what? What? It's good. My imports. My names, right? Homework problem or whatever. Pair programming problem. Okay. And then what? What are the tasks that I'm doing just for part of it? Do you need a defined function? We'll do that eventually, but I'm thinking just generally, what tasks? Before thinking about how to do the test, what tasks am I doing? I need to load the data. Okay, what else do I need to do? What's that? That's definitely a part that we have to do, but just thinking only about the tasks like it says from there. So there will be a lot of subtasks in what we do. And I've heard things about, defining variables, size of the data, stuff like that. That's really important too, but I want to be one step above it right now. I want to think just about what will I have to do to take a derivative and put it on this array. Okay, good. So in order to take partials, so I know that that'll be down here. Take partials. Or another way of saying that is, do this subtraction. Good. But in order to do that subtraction for everything, I will need.
Do you need like a list or an array to put the data in?
Okay, I'll need that as well. I need to generate lists. That's kind of like part of the variables part. So we will need both of those. But I'll also need a for loop. Okay, so I'm identifying the key structures before I identify what I need to fill them with. So here, the technique is walking through the entire array, either starting at one end and walking all the way through till I get to the end. And then guess what? I have to go down. So this must be how many for loops? 2. I have to use one in X and one in Y. Okay, so I do 2 for loops, right? One in X and Y. Good. And now that I have that in my mind, I know that I have to load the data. I have to have multiple for loops. I have to take the partials that I'm, interested in, and I can fill in the details after that, right? One of the details being, okay, I should probably define variables and arrays. Does that make sense? Do I need a user-defined function? No. That's always important. It's not always a no, but it's not always a yes, right? And there's a little bit of like art to knowing the difference. Do I need a while loop? Doesn't look like it. Do I need an if loop or an if condition anywhere? Why, yes, Alfred.
Only take the central derivative for the ones that are not yet.
Right. Okay, so we might need to be a little careful. Okay. You can do that a couple different ways. As you begin to code it, it will scream at you and get very mad. Okay. Let it get mad at you. Don't anticipate the problem, but know that I'm warning you about the problem now. You could, of course, anticipate the problem and say, well, instead of starting at 0, I'm going to start at 1. That's a perfectly good answer, right? But if you I don't know, if you want to see a break, you can break it. Okay. Does this feel like a good start to the problem? You see how I laid it out? You see how I would do this for myself on paper every time. It takes a little bit more work, but if you have a couple heads and you put the heads together and you say, okay, not just talking about exactly writing down what you need and what it's used for, really thinking about going from the word problem to the algorithm, like, okay, I'm going to solve, this is the math I'm going to solve, and then this is the order in which it needs to be solved in, and then you can start coding. Does that make sense? Okay. Okay, well, I droned on for 30 minutes. So usually that's about as long as people have attention for when it comes to coding. So let's try it. And when you get to the end of point A, let me know, and then we're going to talk about how to game plan for part B. Does that seem reasonable?